Hello everyone, my name is Stefanos Voulgaris and today I am presenting our work from the National Technical University of Athens. The title of our presentation is Neural Network Constitutive Modeling of Soil for Resilient and Sustainable Design. In civil engineering, we often treat materials like steel or concrete with well-defined, predictable laws. However, the ground we build on is far more chaotic. Today, I want to show you how we are moving away from traditional mathematical approximations and we are embracing a data-driven approach to model this complex material, ultimately leading to safer and more sustainable infrastructure. Let's begin by defining the problem. Why is modeling soil so difficult? Unlike manufactured materials, soil is a porous, multi-phase medium. Its behavior is highly nonlinear and depends heavily on three things: its stress history, its density, and its drainage conditions. If you look at the graph on the right, you see results from triaxial tests performed under different confining pressures, for example 100, 200, and 300 kilopascals. Notice how the peak strength, the highest point on those curves, increases significantly as the confining pressure increases. This pressure dependency is a fundamental characteristic of soil. However, traditional constitutive laws struggle here. They often rely on yield surfaces and flow rules. A major issue is that for soil, the direction of plastic strain often does not align with the yield surface normal. This is known as a non-associated flow. Capturing this mathematically is messy and computationally expensive. Furthermore, we need to predict behavior under seismic conditions. This means cyclic loading, loading, unloading, and reloading. Capturing the hysteresis loop generated during an earthquake is essential, but extremely difficult for classical models. So, what is the solution? We propose bypassing the rigid mathematical assumptions of plasticity theory and instead utilizing artificial neural networks. We treat the neural networks as a universal function approximator. Instead of us telling the model how the soil should behave based on a theory, the neural network learns the relationship between stress and strain directly from laboratory data. There are three distinct advantages to this approach listed here. Automatic hysteresis capture. The network inherently learns the complex unloading and reloading paths found in cyclic loading without us needing to write complex branching equations. Eliminating assumptions. We no longer need to define a yield surface or a flow potential function. The data defines the yield point. And memory storage, perhaps most importantly. Soil has memory. Its current strength depends on what happened to it yesterday. The hidden layers of our neural network provide a state measure that effectively stores this stress history memory, allowing the model to understand path dependence. Of course, a data-driven model is only as good as the data you feed it. For this study, a model was trained using high-fidelity data derived from triaxial compression tests. We utilized datasets that capture both monotonic loading, pushing until failure, and crucially cyclic loading, which you can see in the graph on the right. To ensure the neural network learns effectively, we implemented two key pre-processing steps: data normalization. Raw stress and strain values vary by orders of magnitude. We normalized these inputs to ensure convergence and numerical stability during the training process. And secondly, time history. As I mentioned, soil is path dependent. We cannot just feed the network random data points. The data points are ordered chronologically. This teaches the network the sequence of events, that point B follows point A, which is the only way to model the sequential nature of soil response during an earthquake. Now, let's look at the performance. This slide shows the validation of our trained model. The green line represents the experimental curve, the ground truth from the laboratory. The green markers represent our neural network's prediction. As you can see, the fidelity is exceptionally high. The model didn't just learn the peak strength, it learned the entire path. It successfully captured the initial stiffness, the peak, and the softening branch. More impressively, look at the unloading branches at the bottom. The model correctly predicts that when you release the load, the soil doesn't just go back to zero, it retains plastic deformation. This proves that the neural network has successfully mapped the nonlinear relationship for various confining pressures. Now, let's dive deeper into the specific mechanical behaviors the model captured, particularly regarding seismic resilience. There are two critical phenomena we focused on. First is cyclic mobility. In the previous slides, you saw loops. Those are hysteresis loops. The area inside those loops represents energy dissipation, or damping. A model accurately predicts the shape of these loops and, crucially, the stiffness degradation. As you cycle soil, it gets weaker and softer. The neural network captured this progressive loss of stiffness perfectly. Second is effective stress collapse, or initial liquefaction. During an earthquake, pore pressure builds up and effective stress drops. When effective stress hits zero, the soil turns into a liquid. Our model is able to track this degradation cycle by cycle and accurately predict the number of cycles required to reach that failure point. This capability is vital for predicting when a building might tilt or sink during a tremor. So, the title of this presentation mentions sustainable design. You might ask, how does a soil model relate to sustainability? It connects through efficiency and risk reduction. We have identified three pillars of impact. First, risk reduction. By reliably predicting liquefaction and ground failure, we design safer infrastructure. Preventing a catastrophic failure is the ultimate sustainable action, as reconstruction is resource intensive. Secondly, optimized design. This is key. When we use simplified models, we have high uncertainty, so we use massive safety factors. We over-design. We use too much concrete and too much steel in our foundations. With accurate neural networks predictions, we can tighten those tolerances, reducing material consumption and carbon footprint. And third, efficient simulation. The neural network model provides a robust alternative to calibrating dozens of parameters in complex classical models. It simplifies the workflow for engineers, allowing for more iterations and better optimized designs. Now to conclude our findings. Data-driven modeling using artificial neural network is not just a theoretical exercise. It is a highly viable and powerful alternative to traditional elastoplastic constitutive laws. We successfully demonstrated that this approach captures state dependency, pressure dependency, and path dependency simultaneously, something that requires incredibly complex mathematics in traditional mechanics. Looking to the future, we aim to expand this work in two directions. Data integration, we want to combine our lab data with in situ field measurements to create site-specific models. And complex stress paths, we plan to train the model on torsional shear data to understand how soil behaves under twisting and multi-directional loading, which is common in 3D seismic events. And thank you all very much for your attention. I am now happy to answer any questions you may have.